speaker we should also thank because he is willing to speak at 9:30 on Monday morning right after vacation. We have Reid Barton from the University of Pittsburgh speaking on formalizing O-minimality. So thank you, Reid.
All right. I first want to just echo the thanks to you all for being here so early on Monday morning. And also let's thank Rob and Jeremy, of course, again, for putting together what I'm sure will be a great conference. Yeah, so this talk is a little bit unusual in that I think rather than talk about something, a project that I worked on or a project that I'm in progress, is really a talk about a project that I want to do, but one for which I could use the help maybe of some of you, especially maybe more computer science-minded people. So let me explain as soon as I figure out how to get to the next slide. There we go. Okay, so Johan Kommerlin and I have been interested in this subject of O-minimal structures, which I will explain in the course of this talk. We come from sort of different backgrounds. Johan Kommerlin comes from algebraic geometry. He organized a summer school on O-minimal structures in September. I also actually only learned about this entire subject this past September while preparing another talk that was quite unrelated to this one. And I'm coming at it from the viewpoint of a homotopy theorist who's sort of seeing this as a better foundation for doing some homotopy theory. And there's a very excellent book here. I don't know how you can see it just fine. It's called Tame, Topology, and O-minimal Structures by Van den Dries. And as you can see, it's not a very big book, and probably less than half of it is really relevant to the kind of stuff that Johan and I want to formalize. This is just a made-up estimate. Maybe there's like 40 pages of content that I'd like to formalize from this book. This book is very uncommonly thorough in its proofs. Everything I think is really written down in here. In terms of mathematical prerequisites, there basically aren't any. It would be good maybe to have some points of topology. It would be good to know like what an ordered field is. And then I claim that probably it's constructive for people who are interested in this subject constructively. I think actually it's quite interesting if you're a homotopy theorist that this can or probably can be done constructively. And maybe formalizing it would be a good way to sort of demonstrate whether or not it is constructive. And finally, the reason that I'm giving this talk, I guess, is I claim that this subject is not really feasible to formalize by hand without some kind of specialized automation. And I'll try to make this clear over the course of the talk what kind of automation I have in mind. But basically, you should imagine that this is 2018, and I'm Kevin, and I want to prove that 2 + 2 = 4 in the real number, and I don't know how, and I'm going to be really frustrated because every line of my proof is basically I'm in this situation. Okay, so that's the overview, or that's the background story. The overview of this talk is I'm going to talk about what O-minimal structures are, about tame topology, about why I'm interested in this subject, and then I'll go into more detail about the sort of problems that arise when you try to formalize it. And I should also say that this introduction is going to be from the standpoint of homotopy theorist. I'm sure that if Johan gave a talk on O-minimality, it would probably, he's an algebraic geometer, it would probably be a completely different introduction. And the subject really has its roots in model theory, which again, if a model theorist gave a talk on the subject, probably again would be completely different. But since I'm a homotopy theorist, I want to start with some very simple homotopy theory. So this is really the most basic concept of all in algebraic topology. We have a topological space, and we want to study paths in the space. So if X is a topological space, then we have 2 points. We can talk about paths from A to B. It's just a continuous map from the closed unit interval to X that sends 0 to A and 1 to B. And there are operations we could, if we have a path from A to B and a path from B to C, we could compose them to get a path from A to C. In the obvious way, we do the first one and then the second one, and we speed the whole thing up so that it only takes a total of 1 unit at a time. Okay, and if you look at any textbook on algebraic topology, you'll probably see a diagram, a sort of cartoon image of a path, which looks very similar to this one. Maybe because it was very easy to create this in Pixie, I don't know. But I think pretty much they all have this form. Here's the unit interval, here's X, which was represented by some kind of blob. Here's a path, it looks like this nice smooth arc, and that's great. And this is sort of the picture we always have in mind when we imagine what a path is in topology. But if you take a class on real analysis, you'll find out that in general, this is not anything what like a general path looks like. So a continuous map can be quite pathological. And in fact, in some sense, almost all continuous paths are very pathological. So for example, if X is Rn, then the continuous map might be nowhere differentiable. In this previous picture, I just drew this nice smooth curve. but in fact, that's completely unrepresentative. And almost all paths are nowhere differentiable, in fact, in some sense. So you might care about this if you want to relate like the differential topology of X to the homotopy theory of X, or you might not. I'm not sure. Other things that can go wrong. Actually, we could take like X just to be so that it's compact. I'll take the n sphere. I can find a continuous map that hits every point of X. And that's pretty counterintuitive, but it's true because of the existence of space-filling curves. And there's actually not a serious problem, but it actually has an impact on topology. We'd like to prove that Sn, the sphere, is simply connected. How do we want to do that? Well, look at a loop in the sphere, then it should miss a point. And so remove that point from the sphere and contract the rest down to a point, and that's the contraction of your loop. But you can't do that argument because the curve could hit every point of the sphere. So you have to make some first auxiliary argument to take care of the fact that you can locally look at some place where you could deform the path so it doesn't hit some point, and then you can do the argument that you really want to do. So that's another sort of thing that can go wrong. Obviously, the second class sort of is contained in the first class. And another thing that would go wrong, let's say you want to prove the Van Kempen theorem. You have a space and you cover it by two, let's say, closed sets. And let's suppose you understand paths in A and you also understand paths in B. You want to understand paths in X. Well, you'd like to say, well, okay, the path is probably, what's the path going to do? It'll be an A for a while, and it'll be B for a while, and then it'll be an A for a while, something like that. But that's also not true, because the path could wiggle back and forth between A and B infinitely many times. Here it only happened countably many times, but I could give you even worse examples where there's like a Cantor set of places where it crosses sort of the line between A and B. So that would obstruct sort of like the proof that you'd want to do again of Van Kempen's theorem. And so I think Van Kempen's theorem is only true if you cover it by open sets, and then in practice, you really want closed sets, so you have to take some tubular neighborhood that deformation retracts onto the sets you really want. And again, this is an extra step that you don't really want having your proof. And so I want to emphasize that all of these situations that I just listed, X, the space X itself, is completely, I mean, it's just like a manifold, smooth manifold or something. It's the best kind of possible kind of space. The issue is not with the space X. It's with the kind of paths that we are considering. But it's also true, of course, that X could itself be sort of not very useful for homotopy theory. For example, we could take the p-adic numbers, they're topologically a Cantor space. That topology is really important if you do algebraic number theory. It's really useless if you do homotopy theory, because there aren't many paths. It might as well be discrete. And we'd rather just this object not exist because it doesn't have any relevance to the theory you want to do. So this is sort of ways in which topological spaces, they don't really, I mean, they are adequate. Obviously, you can do homotopy theory of topological spaces, but they somehow aren't well suited to the actual problem you want to study. So Grothendieck has this sort of research program that he laid out in 1984, and he wrote at length on this. So he says, after some 10 years, I would now say with hindsight that general topology was developed during the 30s and 40s by analysts, and in order to meet the needs of analysts, not for topology per se, i.e. the topology, study of the topological properties of the various geometrical shapes.
Schultz has also said that the notion is completely wrong.
Right. In fact, he's talking about the sort of, right. So this is related in spirit to that. It goes on to say that the foundations of topology are inadequate is manifest from the very beginning. I gave you these very basic examples in the form of false problems, at least from the point of view of the topological intuition of shapes, such as the invariance of domains. The invariance of domains is the statement that Rn and Rm are not homeomorphic if n is not equal to m, which is again a geometric statement that looks obvious, but because of the existence of space-filling curves and things like that, it's actually quite difficult to prove. Even if the solution to this problem by Bauer led him to introduce new geometrical ideas. So he goes on to try to make the case for a setting for doing topology. Well, I guess I'll just explain it this way. Develop a setting for doing, say, studying the homotopy theory of spaces, which is akin to topological spaces. In particular, it's flexible enough to allow those kinds of constructions that we'd like to do with topological spaces, like taking two paths and composing them, but also tame enough to rule out all those bad behaviors that we saw on a couple slides ago. Okay, so this is the sort of not very precisely posed problem that we'd like to solve using, well, whatever comes to mind. So one setting in which you can do this is in semi-algebraic using semi-algebraic sets. This comes from real algebraic geometry. So I'm going to fix a real closed field R for a little while. If you don't know what a real closed field is, you can take the real numbers. That's a real closed field. If you're a constructivist, you might prefer to take the real algebraic numbers. Actually, I'm not entirely sure whether there are necessarily any other examples of real closed fields. I think there are, but I'm not entirely sure. Are there? Yes, there are. Okay, great. Thank you, Sarah. And, well, we'd like to define we'd like to look at subsets of Rn that are sort of describable in a nice way. So in particular, we're going to look at sets that are cut out by a combination of polynomial equalities and polynomial inequalities. And so X here is a sort of vector of n variables. The F1 through Fk and G1 through GL are polynomials in those variables with coefficients in R. And I look at sets that are this form, and I form finite unions of them. And often people just have one function f because you can express the first k conditions as the condition that the sum of squares equals 0 because you're in an ordered field. But that's sort of an encoding trick, so I didn't bother to do that. And we also want to talk about functions between them. And so if we have a semi-algebraic set x and a semi-algebraic set y, they're sitting in different Rn's, then a function is semi-algebraic if its graph is just a semi-algebraic set in R cross n. Okay. And in topology, we'd mostly be interested in continuous semi-algebraic maps. But we can first just talk about semi-algebraic maps and then impose continuity just by R as a general real closed field, but you can just use, say, the standard on delta definition of continuity, and you'll get a very useful concept. So the claim is that this setting solves all the problems that I listed earlier. So first of all, a semi-algebraic function is differentiable at all but finally many points. I didn't even have to assume it was a continuous function. It's automatically continuous as well at all but finally many points.
Something like sine is not semi-algebraic.
Correct. Sine is not semi-algebraic. Yeah, and I can come back to that later example again later. So the second issue was this existence of space-filling curves, and that's impossible in the semi-algebraic setting because there's a theory of dimension that takes a semi-algebraic set, spits out a natural number, which is what you think the dimension should be, and it has the property that the dimension of the image of a set is a bit larger than the dimension of the original set. So I can't possibly map the unit interval, say, onto a sphere Sn for n greater than or equal to 2. So that means I could do the argument I wanted to do to prove that the sphere is contractible, or sorry, simply connected, without having to jump through these additional hoops. And the third one was that, if I have a space that's covered by two closed sets, then I had these paths that would wiggle back and forth between them infinitely many times. That's also impossible. So now if I cover my space by two closed sets, they're also semi-algebraic, then if I look at any path in X, it only switches between A and B finally many times. So then I can break it down into a composition of some finite number of paths, each of them belonging to either A and B, and then I could do whatever argument I want to do about those paths. Maybe none of this is really very surprising because semi-algebraic sets are so special. The other point, which is relevant, of course, for homotopy theory is that we can look at the homotopy category of semi-algebraic sets, and it actually agrees with the thing that we were interested in the first place, namely, well, almost. It agrees with the homotopy category of finite CW complexes. I had this condition that the semi-algebraic sets were finite unions of these basic ones. But in any way, there's certainly only like a small set worth of semi-algebraic sets total, and there's a large family, collection, class, whatever, of CW complexes, so they can't possibly really agree with each other. But we get the finite ones. And so as a homotopy theorist, I would very much prefer this word finite was not here. There's another theory called the subject of weakly semi-algebraic spaces, which is sort of a carefully controlled, filtered colimit of these semi-algebraic sets that corrects this issue. So you really get like the entire homotopy theory of spaces. This is not what I'm going to talk about in this talk, but it builds on top of this semi-algebraic set theory. So in order to formalize this other subject, I first need to formalize this semi-algebraic set subject. So if I just return quickly to this list of properties, I think these properties are maybe not so surprising in algebraic sets. But what I think is very remarkable, and is the subject of this book again, and of the subject, is that all of these theorems follow from a very short list of axioms about the family, the class of all semi-algebraic sets. So originally, historically, I think all these theorems were proven probably one by one for semi-algebraic sets. And then I think basically the author of this book, Ben Dundrees, figured out how to take all of the proofs of all these theorems about semi-algebraic sets and reduce all the arguments to just a few axioms that control the entire theory. And so that's what the subject of O-minimal structures is all about. And more specifically, semi-algebraic sets are an example of an O-minimal structure, and all these theorems are valid for, there are some technical hypotheses, an O-minimal expansion of a real closed field. And I will explain what these words mean next. Okay, so we're going to start out with just a structure. This is sort of a concept from model theory, but it might not be the one that you're used to if you're a model. I mean, you probably also know this concept, but if you're just taking a class on model theory, it's probably not that kind of structure. So we fix any set R. The literature always insists that R is not empty. I don't think it matters. So a structure is going to be, so for every n, I'm going to tell you which subsets of Rn I will call definable. And in the case of, so an example is going to be that the definable sets are the semi-algebraic sets. And they have to, these sets have to satisfy, or this family has to satisfy this list of conditions. So first of all, the first one is about what happens if I look at subsets of Rn for a fixed n. They should be closed under the operations of taking the union, taking the intersection, taking the complement, taking the empty set, and so on. Finite, yeah, so it's finite unions, that's right. The second one, well, the rest of the conditions tell me how I can relate subsets of Rn in bearing. So if I have a subset of Rn that's definable, then I can cross it with R on either side and get a subset of Rn plus 1. That's, again, has to be definable. There's a subset where I insist that two of the coordinates are equal. That's a definable subset. And finally, the projection of a definable subset, if you project out one of the coordinates, is still definable. These conditions are in the form, I've written them in the same form that they are in this book. They're in a sort of, this is kind of a logically minimal, I guess, set of axioms. Obviously, I think there's no situation which you would really have an easier time proving smoothly x1 equals xn is definable rather than xi equals xj. But so that all the obvious, well, it's a fairly easy exercise that all the obvious variants of these conditions are also implied by these axioms. So I could have written xi equals xj. I could have projected out any one of the n plus 1 coordinates, not necessarily the last one. I could have inserted a copy of R anywhere, not necessarily at the beginning or the end.
How is an algebraically closed field a constructible set?
Sorry?
Sense of algebraic geometry.
Yes. Right. That's right. Well, they form a structure, yeah. Okay, and so just so that I get to the definition of O-minimal structure, I'm going to impose some more structure on R. I'm going to say it's an ordered field. And then I'm going to say, I'm going to use the phrase O-minimal structure to mean that I'm assuming that R is an ordered field. This is not necessarily the standard convention, but it's just shorter than saying O-minimal expansion of a real closed field or whatever. And I want to add a few more conditions. So first of all, I want all the constants to be definable. So every singleton set is a definable set. I want extension, meaning it extends, the structure extends the operations which are already defined on R. So I want the relation, the inequality relation to be definable. I want the graphs of addition and multiplication to be definable. And finally, the minimality condition, which is the really only interesting one, is that any definable set in R is a finite union of singletons and open intervals. And I don't know whether it's obvious yet. Hopefully, it will soon be obvious that singletons and open intervals, by everything that came before, are automatically definable. And so this is just saying that the class of definable sets in R is as small as it can possibly be, given everything that came up to this point. So this is the definition of an O-minimal structure.
And there's many on the real number.
Yes. So for example, if I look at the semi-algebraic sets, those form an O-minimal structure over any real closed field. There's only one condition which is not obvious, which is that when you project a semi-algebraic set, you get another semi-algebraic set. I wasn't planning on talking about this, but luckily I looked at the program, and I think that there is at least one talk which is very related to this theorem. So I encourage you to go to it and find out everything about how to prove this theorem. I hope maybe that it will be as I say. There are other examples. For example, on the real numbers, you can add the exponential function to your structure, and you still maintain this O-minimal property. And I was going to add, I forgot to add the sort of non-example that Kevin actually kind of already alluded to. If I add the graph of the sine function from R to R, it cannot be a part of any O-minimal structure, because I could look at how it intersects the line y equals 0, and I would get an infinite set of single. It wouldn't satisfy this last condition. So it's really quite a strong condition to say that you have an O-minimal structure, and this theorem is, I think, pretty remarkable. There are other examples that are called sub-analytic functions or sub-analytic sets or something. I'm not sure exactly what those are. But these are some examples. So I think this first example would be the easiest one to formalize the existence of, and I don't think it's very easy, but the advantage of generalizing over all O-minimal structures is that I'm absolved from the requirement to actually produce any example of one. So I can do my whole entire theory without actually proving any hard theorem. So of course, we also want a corresponding notion of definable function. And so we'll quickly get to the point where I want to make some argument that I would like to formalize, and it will be ugly. So we're going to define this notion of definable function just the same way as I did for some algebraic functions. So a function is definable if its graph is definable. Okay, and then maybe probably the first thing I'd like to prove is that the composition of definable functions is definable. Okay, so well, here's sort of the proof more or less. I'm going to, just for notational purposes, I'm going to assume that my functions are just f from R to R and g to R to R. In general, I would look at a definable subset of Rm, Rn, and Rl or something, and I would have two functions, definable functions between them. And then I need to prove that the graph of the composition is definable. Okay, and I did it by this calculation. So the graph of the composition is the set of all pairs. So z equals g of f of x. And I need to somehow relate that to my original givens. And the way I can do that is I can introduce this extra variable y, which is supposed to be f of x, and then project away y at the end. So I know that for every point in that first line, there's going to be a unique point. It doesn't have to be unique, but it is unique on the second line, namely one where I take y as f of x. And then to pass the third line, I've just sort of written this set as an intersection of two other sets. And then I notice that this first set here is the graph of x, the graph of f crossed with r. And the second set is the graph of g crossed with r on the other side. And so now I've written the graph of the thing I'm interested in as sort of in terms of the operations, the axioms of an O-minimal structure. Or really just a structure, period. I'm not using O-minimality yet. And therefore, the graph of this function is definable. So there was some procedure that I applied to get from sort of the definition of the composition of functions to this formula here that if you just wrote down this formula, no one would know what it was. And I claim that this style of proof is not sustainable. Like, you cannot formalize this like, this is not the right language in which to talk about the subject of definable functions, of any of the things that you'd want to do in this area. So this is just one example. Let me give you a sort of less trivial example. So first of all, if R is, well, say if it's a real closed field, for example, but also just if it has a total ordering, which is definable, then we can give Rn the product topology of the ordered topologies. And then I claim that if I have a definable set, its interior is also definable. Okay? I'm supposed to prove this using the axioms of an O-minimal structure, or just of a structure, plus the axioms, the conditions here, that the ordering is definable. So how do I do that? Well, I know that a point is in the interior of A if and only if there's a base of the topology that consists of these rectangles, right? And so I need to find an element of that base that contains my point, right? And such that every point in that base element belongs to A. So I wrote down this really long formula that involves the inequality, and it involves A itself. And I claim that this is the end of the proof, right? This is like Kevin's, like, I'm done, right? Whenever you get to this point, it's not on the subject, you are done. And this is where I claim that you need some automation that fills in what happened here. Reid is not going to accept this as a proof, but I accept it. So I accept it as a proof. So there's some barrier that needs to be crossed here. So why do I know that this works? Well, there's a theorem. This is the model theory basis. This is a theorem which is underlying the definition I gave before. This is the real definition of a structure. If I have any formula of first order logic that involves a bunch of relation symbols and a bunch of function symbols, and I tell you how to interpret every relation and function symbol as a set of like R to the appropriate arity, and if all those interpretations are definable, then the interpretation of the entire formula is definable.
Exists is the projection.
Exists as a projection, exactly. So in order to prove this, you might first want to say eliminate all the function symbols by some standard argument where you just turn them into relation symbols and introduce more quantifiers. And then after you do that, you have some, you can do some structural induction on your formula. If you see an existential, you turn into a projection. If you see an and, you turn it into an intersection. At some point, you'll get down to a relation symbol applied to a bunch of variables, but they might not be the right variables. Right? So you know that R is a definable relation, and now you have to prove that R applied to some subset, maybe repeated variables in the wrong order or whatever, is also definable, and that's going to use the other axioms of a structure. Okay, and so this is exactly what you need to make this argument sort of a complete argument. And so in order to do this in a proof assistant, you need, I think, something. I claim. Pretty already, I see, disagrees.
No. I'm just wondering whether you will say reflection on one of the later.
Well, I will say it verbally, but not on a slide. It would be nice to have some kind of automated procedure that will take a goal that's in the form, I want to prove that some set is definable, and it will just prove that it's definable using whatever hypotheses are in the context. So you might argue, I can sort of cure Mario in my mind already. Well, you do really need a tactic. It could be that you just sort of like do the basic library of all the sort of 20 different lemmas that you need to prove about, you know, the composition of definable functions and the interior of a definable set and the pre-image of a definable set and all these things. And maybe if you know, once you write down that entire library, you're sort of done, and then forever you just sort of use your library. So I claim that this is not the case. I can't really necessarily convince you of this fact, but it's my opinion. I want to give you an example where you actually use the O-minimal structure. So this is the sort of, this is literally the first lemma in this book where they prove something about a function being tame, and they do it using the O-minimal structure. So here's the most basic statement. So if I have any definable function, again, R is an O-minimal structure, or there's an O-minimal structure on R, and we're being definable in that sense. Then there's some interval that's contained in this domain, which either F is either injective or constant. Okay, so it's definitely not true for T. Well, that does have intervals where it's injective, but it's not true for a for like a Weierstrass nowhere differentiable function. Those are nowhere monotone, nowhere injective, as well as being nowhere differentiable. So there are two cases. So the first case is if we want to look at the sort of fibers of F. So if there's some point that gets hit infinitely many times, well, let's look at its pre-image. Then that set is definable. Okay, that's probably a lemma. And so because it's definable by the O-minimality, that means that that pre-image has to contain an interval, and then that interval is the interval we're looking for. Okay, the other possibility is the pre-image of every point is finite. Okay, in that case, we're going to write down this set. So it's the set of all x that are the smallest element of the set of maps of in the domain, set of points in the domain that get mapped to the same point as it. So in particular, imagine you start with any x prime. Look at what happens when you apply f. That will go to some point. The pre-image of that point is finite. Among those finitely many points, one of them is the smallest. And that smallest point we add to k. You can think of forming k in that way. So from that description, it's clear that like the image of k under f is the same as the image of the entire interval under f. And because the pre-images of f are all finite and the intervals are infinite, that's another lemma that you.
Is that constructed?
That is my next slide. Did you have a question as well? Same question. Great. I need to speak both. So that means that k is infinite, and let's see, where was I? Yes. So k is infinite. So then by the O-minimality structure property again, K has to contain the interval. And then I claim that F is injective on that interval. And the reason is if f of x equals x prime and they both belong to K, then they're both less than or equal to the other one. And therefore F is, therefore they're equal. So I know F is injective. So classically, this is a valid proof. I'm really glad I added this next slide because, I was looking at this and I thought, well, this is kind of awkward because I have this use of the excluded middle, right, at the very beginning of the proof. So I claim that actually, this is not such a problem as it appears, but we need to be maybe a little careful about sort of what we're doing constructively. And probably the experts on this can also instruct me here. In the constructive setting, we want the minimality axiom should be constructive too. So the axiom said that if I've given a definable subset of R, then it is the finite union of singletons and open intervals. I wanted that to be a procedure. So I can ask the system or whatever, I can ask the O-minimal structure sort of to give me that description as a finite union of points and intervals. You can think of it as just the line is divided into by finitely many increasing points, and then for each interval or singleton I get, by that decomposition, I tell you whether or not the set contains that interval or point. So there's a unique normal form for subsets that are of this form, and I want to have access to that normal form. Okay, for that to be possible, I don't want, like in lean terminology, I don't want definable A to be a prop because there's no way I could ever produce this data for you. So definable A could be, for example, the type of all formulas, let's say in the case of some algebraic sets. I can just take definable A to be the type of all formulas whose sort of extension is A. And then I could mod out by the trivial relation if I wanted to, so that it's a sub-singleton and kind of really reflects what I think it should be mathematically. And that data would allow me to do this, to perform this procedure by quantifier elimination or however it's done. I don't really know how it's done, but people tell me it can be done. And then I claim that if I have a definable subset of R0, so that R0 just has a single point, and classically either A would contain it or it doesn't contain it automatically. But in an O-minimal structure, I claim that actually, it's probably better to just add this as an axiom, but I claim that in fact already follows from the other axioms. A is decidable. Well, how do I decide it? I just take R cross A. There's an axiom that I could do that, and it's a subset of R. So I look at whether I apply this procedure. If it's empty, then I know A is empty. If it's the whole line, then I know A contains the unique element of R0. And now, in this previous argument, I needed to decide whether or not there was an interval on which F was constant. And the way I do that just amounts to deciding whether or not this formula is true. This is sorry, I should have said sentence. This is a formula with no free variables. I asked for, that X shouldn't be there. I asked for the existence of A prime, B prime, and Y, such that on that interval A prime, B prime, F is equal to Y. Yeah.
What is it decidable?
Sorry.
What is decidable?
Oh, here? The same thing that it means in lean. But I guess, I mean, constructively, I can.
But what is decidable? Whether a point is in A or not?
Yeah. A is a sub-singleton already. So I can think of it as a truth value, right? It's a subset of O. Does that answer your question? Yeah. So in particular, like another way that you could think of this as whether A is empty or not, because if you're given A, you can always just project away all of the variables to get a subset of R0. That's what I did here by introducing these unique existentials. And that would give you a set which was inhabited if and only if the original set was inhabited. And you would check whether it's decidable. Okay, so this is actually sort of where I'm up to. Just to finish that, I guess, here we're doing a case analysis. But the case analysis is on this proposition, whether or not, well, I wrote F inverse of Y is infinite, but I really meant contains an interval. I can say after the fact and then apply this argument. It works the same way. So my question now is sort of, what is the best way to, well, let's go back to just sort of say this slide and maybe following slide. My question for all of you, and maybe by the end of the week, someone can tell me what the best answer to this question is, how to actually implement a procedure like this. So I have, in my mind, this sort of, I thought about this a little bit, not a whole lot. I think that there are sort of two different approaches. In my mind, they're similar to the approaches that the mathlib library has for the ring tactic and the ring 2 tactic. The first thing you might want to do is take your formula. So just to try to clarify a little bit, I'm imagining that S is given by literally a lean expression, right? I wrote literally the set of X, let's say. I wrote basically this exact statement in lean. And I put the word definable in front of it. And I want to say have definable this expression by definability. That's my goal, just to try to emphasize that. And that will use from the context the fact that F is decidable and so on. That's what the tactic should do. So what's the best way to do that? Well, you might want to first sort of eliminate function symbols, like I said before, replace them by relational symbols. That might make later steps a little bit easier. Then you're left with some statement that only involves relational symbols. And then there's sort of two approaches, I think. One is to apply backwards reasoning steps. So if your statement, sort of like Kevin was suggesting, if your statement looks like an existential, apply backwards reasoning step that applies projection. If your statement looks like an and, then apply the intersection axiom. At the end, you're going to be left with a relation that has the wrong variables. You're going to have to do some more work to synthesize, sort of juggle the variables into the places that they should be. The second approach is, so Freek was suggesting, to reflect your expression into some embedded first-order logic syntax. Prove this theorem in the object theory, apply it, have the tactic apply it, and then sort of conclude that what you want to define is definable. So both of these approaches, I think one thing to keep in mind that makes this tricky, I really, really want to be able to apply it to statements that look like this. But the problem with this statement is it's got lots of dot, dot, dots in it. Right. And n here is this is not a theorem schema. So I want to prove this once and for all for every n. So this is maybe something that would influence the best way to solve this problem. So I'm not sure what the best way to do this is. But
what does that mean? You want infinitely many theorems?
No, I want one theorem. I want the first line for all n in that, for all a and n decidable.
Okay.
And then I want, so the point is that whatever the automation needs to be able to work, even in the case where n is an open term. And n is still a variable. Okay, so that's all prepared. So thank you very much.
Thank you, Reid. We've got time for questions. I think we don't need the microphone, at least for the stream. So if you can speak loud enough for your question, just shout. Otherwise, I can bring you the mic. I see a hand from Jeremy.
Well, it's a comment and a different question. So the comment is that in fact, the notion of O-minimality is due to Charlie's Timeline.
Okay.
It was a PhD dissertation under.
Okay.
But so in the early days, O-minimality, definable, was really defined by
right.
And I think Lau, when he wrote that book, he really went out of his way to make it amenable to mathematicians. So he knew that people like Kevin, before Kevin got involved, he was totally didn't like quantifiers and symbols, logical symbols, and so on. So he tried to present it in a way that in terms of projection.
Right.
So I think just a comment that what's nice about the formalization effort is that it's sort of bringing together the mathematics and the logic, making the logic. I guess the question is, so a number of computer scientists in this room will tell you that for real close fields in particular, there's a lot of work on algorithms, verified algorithms, efficient algorithms. And none of the algorithms are really good.
Right.
Is there anything here that you might, do you just want constructive or do you actually want
So I'm interested in constructive. I should have mentioned this earlier. If you look at this theorem, it says that, I mean, as homotopy theorists, we're sort of interested in, say, CW complexes or finite CW complexes or something. But that theory, I think, is impossible to make constructive. As far as I know, this is, you can't even compose paths properly constructively because you would have to decide whether your time was less than 1/2 or greater than, right? So this theory of doing this stuff with topology, I think, is hopeless, constructively. And so the other side, with the homotopy, this homotopy category of some algebraic sets, that part I do want to be constructive, so that I get sort of category that can replace topological spaces, but I could use it in a constructive setting, so internalize to a topos or whatever. That's my personal motivation for just wanting to be constructive and not really caring about the algorithm.
But probably Johan has a completely different motivation. Because this stuff has had, like 10 years ago, 15, Johan Commerland,
Yeah.
this suddenly had huge applications in algebraic geometry, in arithmetic geometry. It was proving theorems that number theorists were interested in, using this weird logic. It was a shock. Suddenly, mathematicians had to learn some number theory, had to learn logic. It was weird, like it's a study group.
Yes, another question?
You mentioned one time that you want this definable A as more of a procedure that outputs not just one Boolean value or kind of another data, right? That gives the
A formula for A.
Roughly, I was imagining that there's a list of formulas that defines all this